All right. On the last page here, we are given a few problems. All right, let's take a look at the first one and read it. We got two runners, runner A and runner B, that run on a straight race track for 10 seconds from 0 to 10. So the graph above, which consists of two line segments, shows the velocity, meters per second, of runner A. And the velocity of runner B is given by this function written down here. V of t equals 24t over 2t plus 3. What a great function that is. And then in A, we're asked to find the velocity of runner A and the velocity of runner B at time t equals 2 seconds. So let's find the velocity of runner A at t equals 2 seconds. Luckily for us, the velocity of runner A is given by this graph over there. This is a velocity graph, so we can just look at t equals 2 seconds and find out that our velocity there would be, well, what you can do is you can find the slope of the line. This line looks like it goes over 3 and up 10. So the slope of this line would be 10 thirds, or 3.3 repeating. And that means that for every 1 unit we go over, we'll go up 3.3 repeating. So then the velocity at time 2 would be 6.6 repeating. So the velocity at time 2 of runner A is 6.6 repeating meters per second. And then the velocity of runner B is found by using this equation that we're given. We're given 24t over 2t plus 3 and told that that is the velocity of runner B. So we can just plug time 2 in for t. 24 times 2 is 48. And then 2 times 2 is 4. 4 plus 3 is 7. So 48 divided by 7. I'm going to reach for a calculator there. Is 6.857. So those are our two velocities of the runners. The next question in B is asking us to find the acceleration of runner A and the acceleration of runner B at 2 seconds. Remember that acceleration is equal to the derivative of velocity, and that's the slope of velocity. So what we're going to do is find the slope of this graph up there to find the acceleration of runner A at time t equals 2 seconds. And the acceleration of runner A at time t equals 2 seconds is the slope of this graph at t equals 2. And we found that up there from the previous example, 3.3 repeating, because we see that the line goes over 3 and up 10. So 10 divided by 3, and we get 3.3. And that would be measured in meters per second. And the acceleration of runner B is a little more complicated. What we're going to do is, because we're given an equation for the velocity of runner B, to find the acceleration of runner B, we're going to take the derivative of that equation. And we need to use the quotient rule here. So we've got low d high minus high d low all over low. So if we were to simplify that out, we'd end up with 48t plus 72 minus, and then 48t all over 2t plus 3 squared. And those 48t's are going to cancel out. And from there, if we find the acceleration at time 2. By just plugging in 2, we'll get 72 divided by, and then we'd have 7 squared, 72 divided by 49, which is 1.46 meters per second per second. All right, let's take a look at the next one. Okay, this question is asking us which graph best represents the position of a particle. This is asking us which graph best represents the position of a particle, s of t. So notice that each one of these graphs is a position graph, s of t. They're not velocity graphs, they're position graphs. And then we're given some information about the velocity and the acceleration. We're given that the acceleration is positive and the velocity is positive. Now, in order to deal with this, remember that the velocity is the slope of position and acceleration is the second derivative of position. So what that means is we're trying to look on these graphs for places where not only is the slope positive, so the slope of the position is positive, but we want the slope of the slope to be positive as well, or we want the slope to be increasing over time. Or another way to see it is we want s of t to be concave up. If the second derivative of s is positive, so if the second derivative of s is positive, that means that our original function s is concave up. And if we go through in each one of these examples, we see that in A, yes, the slope of s is positive, so velocity would be positive here, but the acceleration would be 0 because this graph is neither concave up or concave down. It's just a straight line. In part B, we see some positive slopes again. So the velocity would be positive in this position graph, but the acceleration would be negative because those slopes, those velocities are actually decreasing as you go towards the right. Or you see the position graph is concave down. We're going to skip C for a second, and I bet you probably know why, and look at D. In D, you can see part of this position graph has really steep negative slopes. So that would mean that the velocity is negative, so we don't want D. And then if we look at E as well, we see some negative slopes on here, which means that the velocity would be negative at those times, and we can cross out E from that as well. So that leaves C. C is where the velocity or the slopes of position are positive, and we see that the velocity is increasing as you go from left to right. The slopes are increasing. We see the graph is concave up, so this means that the acceleration is positive as well. Okay. And then in this last question here, we're given the graph of the velocity of a car traveling on a straight road from time 0 to 50 seconds. And we're given a graph of velocity, and a table with velocity as well. And in part A, we're asked during what intervals of time is the acceleration of the car positive? Remember that the acceleration is the derivative of velocity, so we're being asked here, where is the derivative positive? Where is the slope of velocity positive? And if we look at our graph, we see positive slopes right there, 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 right up. And then we see some negative slopes, but we go back to positive slopes along that interval. So we can safely say that the acceleration is positive, over the intervals 0 to 35 and 45 to 50. Let me write that neater. 45 to 50. Because the acceleration is equal to the slope of velocity. All right. In part B, we're asked to find the average acceleration of the car over the interval 0 to 50. So the average acceleration is found by looking at the change in velocity over that time interval. So we're going to do velocity at 50 seconds minus the velocity at 0 seconds over 50 minus 0. What's nice about this particular example is that you don't need to plug in any numbers into an equation or anything like that, because we've got a table up here that tells us certain velocities at certain points in time. So the velocity at 50 seconds is 72, and the velocity at 0 seconds is 0. So we're just going to write 72 minus 0 over 50. So then the average acceleration would be 72 feet per second over 50 seconds, which gives us 1.44 feet per second per second. Or feet per second squared. And our last part, find one approximation for the acceleration of the car at time t equals 40. So at time t equals 40 is right there, and because the acceleration is the slope, what I want to do is approximate the slope at t equals 40. So the approximate slope of velocity at t equals 40. So we're going to set up a few options that you could do. What you could do is you could find the slope between 35 and 40. You could find the approximate slope between 40 and 45, or you could also find the slope between 35 and 45. So let's just find the approximate acceleration. Excuse me, that's not the right way to write it. The approximate acceleration, which is the approximate slope of velocity at 40, which would be approximately equal to, and what I'm going to do is take a look at the slope between 35 and 40. So I would have 75 minus 81 over, so I'm getting those numbers from here, 75 minus 81 over 40 minus 35. Again, this is just the approximate slope. I have no way of knowing the actual slope at 40 because I don't have an equation, but we can approximate the slope by using values from the table. So that would give us negative 6 over 5, which is negative 1.2 feet per second per second. And remember that this acceleration tells us that velocity is decreasing. Because the acceleration is negative, the velocity would have to be decreasing. And you can see in our graph that at 40, you can very much see that velocity decrease at that point in time. Okay, that's it.